mechanical model of the atom is the current accepted model of the atom. The electron moves in only certain allowed orbits around the nucleus, and we'll have a couple things that will affect that, couple properties, quantum numbers that will affect that. The energy of the electron in a hydrogen atom is given by this equation, negative h Planck's constant, c speed of light, rh Rydberg constant, times 1 over n squared. So n is the principal energy level. So this is given the energy of a particular level, and when you run all these constants together, we'll get negative 2.18 times 10 to the minus 18 joules. It's a negative value, so our energy of the electron is going to be negative. If we see that we put in infinity for n, that is when we have ionized the atom, taking the electron completely away. 1 over infinity goes to 0, so the energy of a completely separate electron from the hydrogen atom will be 0. And it becomes more negative as it drops down to the lower levels. If we put the lowest level possible, 1 here, we'll see that the energy of the ground state electron is negative 2.18 times 10 to the minus 18 joules. And we'll see another version of this equation in a little bit that allows us to calculate the energy electron transition between two different energy levels. So when the electron is in the lowest possible energy state, which for hydrogen would be n equals 1, that is called the ground state. If the electron is not in the lowest possible energy state, then it is in what's called an excited state. Okay, we just said this, so the ground state is when the electron is in the lowest possible state. For hydrogen is in n equals 1. So for the electron transitions, whenever electron jumps between energy levels, it's absorbing or releasing a photon of light in the process. The photon of light contains specifically the difference in energy between those two levels. So for two levels, so we'll do our final mass initial, our change in energy. For the hydrogen atom, we do the difference of the energy levels of the two hydrogen atoms. We can also have a form for hydrogen-like atoms. This is the form for hydrogen-like atoms, where instead of 1, we have Z, the atomic number. This means that we could do helium or helium with a +1 charge. Hydrogen-like means we only have one electron present. When we have more than one electron present, the electron-electron interactions change the energy levels some. So in this equation, we're doing final minus initial. So the sign can change here. So if we have a negative energy, it means we're releasing energy. It's exothermic, it's releasing energy. The energy is dropping down to a lower level. Positive energy means that we're absorbing energy. And then once we have the energy, the wavelength of the photon being absorbed or emitted is, of course, E equals h nu, or hc over lambda. We can get the wavelength by rearranging this equation. We get lambda is hc over E. Another variation of this equation for the change in energy levels, we can solve that for lambda, or 1 over lambda. This is the Rydberg equation. So 1 over lambda is equal to the Rydberg constant times 1 over n final squared minus 1 over n initial squared. And the Rydberg constant is 1.096776 times 10 to the 7th inverse meters. Meters minus 1 inverse meters. So if we're doing a transition from n equals 3 to n equals 1 in the hydrogen atom, so we're dropping the electron from 3 to 1, so we're releasing a photon of light. So we can answer this part B question first, is that going from 3 to 1, we're going to be releasing the energy, releasing the light. So to get the frequency, we can start off as calculating the wavelength. We can do this a couple different ways. We can calculate energy first, then convert energy to frequency, or we can calculate wavelength and convert wavelength into frequency. So the path I picked was to calculate wavelength, so 1 over lambda. We have a couple different versions of the Rydberg constant depending on the units. This one is given in nanometers. So we calculate first inverse nanometers, convert it to nanometers. We have a habit like we like to use nanometers when we're dealing with anything close to visible light. Convert to meters, and we are looking for the frequency. Frequency is c over lambda, so speed of light divided by the lambda in meters, so the units will cancel out, will give us a frequency of 2.93 times 10 to the 15 inverse seconds. Very high frequency. We were asking for megahertz, so we have to convert that to megahertz. Inverse seconds is hertz, so hertz is inverse seconds. So a megahertz is 10 to the 6 hertz. So we divide by our 10 to the 6 and we get 2.93 times 10 to the 9th megahertz. To get ionization energy for the hydrogen atom, we can use n equals infinity to represent the electron being completely removed from the atom. So we said that both matter particles and energy particles have the characteristic of being both a wave and a particle. Well, de Broglie gave us a way to calculate the wavelength of matter particles, the de Broglie wavelength. So for the de Broglie wavelength, the lambda wavelength of a matter particle is h over mv. So that's Planck's constant divided by momentum. Momentum is mass times velocity. And when we do this, we want to make sure our units are all canceling out appropriately. Easiest way is to use SI units for everything. So we're able to calculate wavelengths for particles of macroscopic things like golf balls, but the wavelength is most interesting for small particles, atoms, or groups of small groups of atoms. There is another strange property to the universe which Heisenberg defined for us, Heisenberg uncertainty principle. There are pairs of properties that have a limit to how much information we can learn about them. So this particular one is for location and momentum. Momentum is related to energy, but it's slightly different. But momentum and energy, the product of momentum and location, product of momentum times location is a finite number, and that finite number has to be greater than or equal to h over 4 pi. So Planck's constant divided by 4 pi. So if we, let me rephrase this. This delta here represents the uncertainty. So when we make a measurement, we always have an uncertainty associated with it. So delta x is the uncertainty in location times the uncertainty of momentum. This will be greater than or equal to h over 4 pi, Planck's constant divided by 4 pi. So uncertainty, if we knew a location precisely, that uncertainty would go down to 0. As the uncertainty approaches 0, our momentum is going to approach infinity. So the more precisely we know one of these properties, the less we know of the other property. So what this does for us for the atom is that we're actually able to measure energy rather precisely. So the Heisenberg uncertainty principle says if we know energy precisely, we are not going to know location well at all. So these electrons, they're matter particles, but they are also waves. We have done many experiments showing the wave nature of these particles. And one of the wave natures is that when they meet themselves, they will have interference, either constructive or destructive interference. So if an electron meets itself at the same phase of its wave, it will have constructive interference, and its presence in that location will increase. If when an electron wave meets itself, the phase is not a good match, there's a mismatch in the phase, then there can be destructive interference, reducing the probability of finding the electron in that location. And in some locations, the destructive interference is so strong that we do not find the electron in that location. We call that a node where we do not find the electron. So waves often have constraints associated with them. A vibrating string, the constraints are the ends don't move. But even with that constraint, we can get different modes of vibration. So the fundamental mode is where the whole string vibrates up and down. The next mode is where there's a still spot in the center, a node in the center. And the string is vibrating up on one side, down on the other side simultaneously, and then oscillating in the opposite direction. This version here, 2.5, cannot occur because it's violating the restrictions, the end conditions that the end has to remain still. So in the atom, we have the condition that the electron, when it meets itself, has to be in the same phase when it meets itself. So this limits the electron to only certain vibrations within the atom. And those vibrations we're going to call orbitals.